1, 2, 1, 2, 1, 2, 1, 2, 1, 2.
So good morning and welcome to the first contributed session, which is on aspects of theory of satisfiability. We have 3 talks. First one will be given by Neil Tappen from Prague, joint work with Leszek Kolodziejczyk on the strengths of the dominance rule. Neil, please.
Thank you, Olaf. So I'm going to say something theoretical about how you get to proof systems beyond extended resolution, maybe. And I guess the interesting thing is that it comes sort of from practice, the actual system we consider. So this is the outline of the talk. We're going to talk about proof complexity and about refuting CNFs. So the general objects we're considering are proof systems, which are things you write down to demonstrate that a CNF is unsatisfiable, and there's certain natural conditions on those. And here are some examples of proof systems that you know: tree-like resolution, resolution, extended resolution, and then some more technical proof logging things that come from work in SAT solving. And we'll use this definition of one proof system simulating another, which is sort of the obvious thing, and I'll just write it down here. P simulates Q if you can change Q refutations into P refutations on CNFs. We only care about behavior on CNFs. And under this relation, if we write the Okay, found it. If we write the strict inequality, it means there's a simulation in one direction, not the other direction, and this means a simulation in both directions. So we get, there's no increase in systems, and then here we get lots of things that are equivalent to extended resolution. So an application of this is in proof logging, where we can run a SAT solving algorithm like DPLL, and then as a witness that an unsatisfiable formula is unsatisfiable, from this kind of algorithm, it's straightforward to produce a tree-like resolution refutation of the CNF given as input. And there's a similar relation between CDCL algorithms and resolution. You can use resolution for proof logging for CDCL. And then more recently, there have been extensions of CDCL, and the system DRAT has been developed for doing proof logging for that, which is equivalent in terms of proof complexity to extended resolution. So the question is, what happens if you start introducing more techniques to your SAT solvers? Is it always going to be the case that the systems we have are strong enough to use as certificates, such as if you're doing symmetry breaking? Or do you need some new, possibly stronger proof system? So an example of such a system is one developed here by these authors recently, and this is the main paper which we're building on for this work. And they have a system that's as strong as DRAT, and it has some extra machinery as well for doing symmetry breaking and a little bit more. And we're asking, is it actually stronger than DRAT? Or from the proof complexity point of view, the more natural question is it stronger than extended resolution? Because this is a kind of frontier in where we're able to prove lower bounds. Well, it's beyond the frontier, in fact. So here are our main results. So the first one, which I'm not going to talk about, is that if you have a single symmetry and you have this Lex leader symmetry breaking, you can certify this in extended resolution still. Then what I will talk about is the dominant system, which is the one that was just introduced, I just mentioned, is stronger than extended resolution, at least sort of morally. So specifically what we show is that if you take this system, then you can simulate, so it's at least as strong as, some fairly well-studied system called G1, which I'll describe. And this is expected to be strictly stronger than extended resolution for kind of philosophical reasons, let's say. But it's it's what you're going to get. So if you want to show something is stronger than extended resolution, this is about the only way you can do it, by looking at these known systems. And you should think of this as something like showing that a decision problem is hard by showing it's NP hard. So we don't know that P is different from NP, but showing something is NP hard is good evidence it's hard. So it's a little bit like that, although there's
Neil,
less.
What is which is expected? What does it mean? Which is expected?
This is the philosophical reasons, which I won't say so much about. So in the end, I'll say something about bounded arithmetic. And these systems come from bounded arithmetic. And you expect the stronger bounded arithmetic with more induction to prove more universal sentences, because this is the behavior you get in classical arithmetic using consistency sentences. So classically, you can separate levels of induction with consistency sentences. So this does not work in bounded arithmetic or in this setting, but it's kind of the only thing people know that would plausibly work.
But Neil, is it correct to say that expected in the same sense as P is expected to be weaker than NP?
Yes, kind of. I mean, there's less evidence than for that, but this sort of thing. Okay, so what are these proof systems beyond extended resolution? So extended resolution is a very strong system. We don't know any lower bounds for it, so we can't show anything that's really past it. But what can we say? And recall that having a stronger proof system means we want something which has almost always shorter proofs than extended resolution does. So there are three things that people have kind of looked at. So one is called implicit proofs, where you sort of cheat almost by you take an extended resolution proof or something similar, and you just write it in a shorter way. Maybe you can find an exponentially smaller circuit that actually describes the long proof, and then you allow this. Another way is just to use some very strong logic. So you go to full set theory, and you say, can I prove that this is unsatisfiable in ZFC? And if you can, then you write that down, and that's your proof. So neither of these is so well understood. The thing that is fairly well understood is what we're going to talk about, which is we sort of stay in the same world of sequential line-by-line proofs as resolution, but we allow more expressive lines. So in resolution, the lines are clauses, or one could say they're CNFs. We're going to allow proofs where you're reasoning with QBFs. So the ideas that are in the proof can be expressible as QBF. So a QBF can express an idea more compactly than a CNF can. But I emphasize again, we're only refuting CNFs. So although in the middle of the proof, we have these more complicated objects, the actual thing we're proving is just a basic CNF. So the kind of implicit idea it's harder is that this extra expressivity lets you prove more CNFs more quickly. So we've seen what a QBF is. What G is actually doesn't matter so much, but just specifically, it comes from a proof theoretic background. So for historical or technical reasons, it's a sequent calculus. So a proof is a series of sequents looking like this, where these are all formulas. So you have line after line that looks like this, and you start with basic axioms, and you use standard rules, and you refute gamma, which means you end up with a sequence saying that sequent expressing that if gamma is true, then a contradiction. So this is what it means to have a refutation of gamma. Yeah, so all the lines in the middle might have QBFs in, but the last line is just talking about a CNF. So this is this rather strong proof system G. We will break this into levels based on the complexity of the QBFs in the system. So in G0, actually everything is a CNF. There's no quantifiers. In G1, you're allowed one quantifier block in each formula. And in G2, you can have quantifier alternations and so on and so on. So we're just stopping at the first level. So we have sort of low down, we get extended resolution. And then it is expected in the sense I said, that as you do these things, as you add more and more expressivity, you should get stronger and stronger systems. But certainly no one knows how to prove this. But this is the best candidate. Yeah, so this is that was the system we're aiming for. How we want to show something is stronger than extended resolution by showing it is as strong as this system. So let me talk about the system we're trying to capture in this way. So Right. So first of all, to talk about extended resolution, I'm going to present it in a certain way. So we have a CNF delta, and we call it a set of extension axioms if it tells us how to define variables y in terms of earlier variables. And these are the normal extension axioms of extended resolution. So we define each y bit by bit as some kind of formula in earlier literals. You can define quite complicated things in this way. And then here is a proposition which you can read as the soundness of extended resolution. It says that if we have start with some CNF, and then we write down any set of extension axioms, then we preserve satisfiability. And this is easy to prove, because given the assignment to gamma, the extension axioms tell us exactly how to set the new variables y to satisfy delta. So there's nothing much to prove here. So that's extended resolution. Now, I'm going to talk about the new rule added in this BGMN paper. So we'll need the technical idea of a substitution, which is just substituting literals with other literals in a reasonable, well, in a normal way, or maybe you replace a literal with a constant, and that's a partial assignment. And use the standard definitions here. So this means you take the literals in the clause and apply the substitution to each one. This means you do that for every clause in a CNF. And this, applying it to a tuple of variables, means you just change each variable. So these are all natural things. So here is a proposition on which this dominance rule is based. You have a CNF, gamma, and some clause C. You have some extension axioms, and you have a substitution of a certain form. And then suppose you know that this entailment is true. Whenever any assignment that satisfies the things on the left satisfies the things on the right. And so gamma restricted by W means that if you change the, sorry, by omega means that if you change the assignment by omega, it satisfies gamma. And this means if you change the assignment by omega, you get a strictly smaller assignment. So this formula here is supposed to be a CNF representing the lexicographic ordering on tuples of variables. So I'm cheating a little bit by assuming that this doesn't present any problems, but let's assume it doesn't. We have some simple formula for lexicographic ordering. So if you have such things, then gamma and adding C are equisatisfiable. So later on, I'll define the rule which lets you add C under these conditions. So why is this? So so suppose gamma, we'll do the left to right direction. Suppose gamma is satisfiable, then it has a satisfying assignment alpha. We take the minimum assignment. If that satisfies C already, we're done. Otherwise, we want to satisfy this thing. So we know alpha already satisfies gamma and not C. We know that delta are just extension axioms, so it's easy to set the variables y to satisfy this. So we can just do what delta tells us to get this bigger assignment satisfying this thing. But now we have this entailment. We satisfy the left-hand side, which means we satisfy the right-hand side. But then you read through what the entailment tells you about how things work with the substitution. And if you define this new assignment by taking beta and applying omega, which maybe isn't clear, but omega maps x to y variables, beta assigns y variables, so this defines an assignment to x variables. So it's the right kind of thing to be a new kind of alpha. So you define that thing, then if you work through the definitions of what these restrictions mean, you get that this new assignment is going to satisfy gamma. That's what this thing satisfying gamma restricted by omega tells you. And also that the new assignment is going to be strictly smaller than the old assignment. So again, this is just working through the definitions of a substitution. So once we have found the minimum assignment, then there's a fairly simple process to get our new assignment satisfying gamma and C. And the system, so they introduced this system in the BGMN paper. I'm going to talk about a simpler system based on the two rules I just described. So we have the system, it's for refuting CNFs, and it says you can use extended resolution to refute your CNF gamma, and you can also use the dominance rule, which looks like this. So this is more or less the same thing as we saw. we will use it if you've derived gamma, maybe by extended resolution rules, and you have all these things, then you can add C to the set of clauses you've derived. So we have these basically two rules we can use. So the one kind of significant change from the proposition is in the proposition, I just stated you happen to know this entailment is true. To make this kind of concrete rule that you can check correctness in polynomial time, we actually have to include a proof of this entailment. And there's some technical issues here with actually showing how you prove entailments rather than refutations in extended resolution, which I will not talk about today. So this is just a dominant thing again. So just to compare this to the system in the other paper, the other system has a lot more machinery for doing things in a practical setting. So it can talk about optimization, which we've removed here. It can talk about linear inequalities, and it can talk about more general orderings. We don't have those, but our system is clearly simulated by theirs. So any lower bound for D is going to give a lower bound for their system. And in fact, in the paper, we show that D is equivalent to G1, giving this lower bound for their system. And in fact, if you take their system and you remove this last thing about more general orderings, you get a fairly, well, or you restrict the orderings they have in a natural way, which is more or less what they actually use in their practical examples, then you get that their system is actually equivalent to D and to G1. So it's reasonable to look at the system D, which has just this extended resolution and dominance rules. So there's two key intuitions in this talk. The first one is that to understand the strength of a proof system, it's enough to understand how much logic is needed to prove a sentence saying it's sound, where, I mean, in some particular logical formal systems. So why are these rules sound? Or how much work do you need to do to show these rules are sound? So for the extension rule, it's easy. So I'm going to talk about the computational complexity of finding something is sound, which here means supposing we do have some alpha satisfying gamma, how do we convert it into something satisfying the other thing? Do we need to do a lot of work, or is it simple? And in this case, as I kind of said, it's polynomial time for the extension rule. For the dominance rule, we can ask the same question. If you have something satisfying gamma, how do you change it to get something satisfying gamma and C? This is what soundness tells us. And this looks harder. So here's a proof of it again. And I guess I'll just draw your attention to this thing about the minimum assignment. So part of the work we need to do if we're using this proof is to find a minimum alpha in some set, the set of assignments satisfying gamma. So in the worst case, I guess this is exponential time, and this is probably bad. But in fact, it's not that bad. So here is a well-studied computational problem of finding a local minimum in a set. Well, local minimum means you don't want to find the thing that's globally smallest, but you want to find a thing that's smaller than its, that doesn't have a smaller neighbor, where you have some particular function that tries to find a smaller neighbor staying inside the set. So n is supposed to stay inside the set and move to something strictly smaller. And the problem is just to find some element of the set where this fails. So this is a well-studied problem in this class TFNP. And it's expected to be harder than polynomial time. Although again, if NP equals P, this all collapses. So to do this complexity version of showing the soundness of the dominance rule, you don't actually need to find a global minimum. You just need to find a local minimum in the sense I just described of this PLS problem. So what is the reason for this? So again, here is the dominance principle. Here is our instance of PLS. The set of things we're looking at is a set of assignments satisfying alpha. And we know a way of moving to a smaller neighbor, which is this function that we used in the proof. So let me go back to the proof. Right. So in the proof, I said we take the minimum assignment satisfying gamma, and then we get a contradiction by constructing this new alpha prime, and then saying there's a contradiction because alpha prime is actually strictly less than alpha that we started with. But you can kind of see that actually here to solve this problem, to find alpha prime, a suitable alpha prime, this local minimum is enough, because we know in advance this neighbor function that's searching for the smaller thing. Namely, it does these things here. We extend alpha to this beta, which we could do in polynomial time, and then we apply omega to get our new assignment, which we can do in polynomial time. So here we're fighting against a particular thing, trying to find a smaller function, and so a smaller string. And so this is actually in PLS, solving this problem, this soundness problem. So we could do it in PLS. And then the thing I guess I won't prove is that the converse direction also holds. So written here as a lemma, given any instance of PLS, if you can solve the soundness problem for the dominance rule, then you can solve the instance of PLS with a polynomial time overhead moving from one to the other. So in TFNP terms, these are equivalent problems. And it's because the dominance rule is pretty general. So you're able to smuggle any neighbor U function you want into it. So this is a way to give some evidence. Really, this is just an intuition and doesn't really play a role in our formal proof that this system D is stronger than extended resolution. Because if we're looking at soundness as this computational problem, then in extended resolution, soundness is polynomial time, whereas in our system D, which has the dominance rule, soundness is PLS complete, which is presumably stronger than polynomial time. So this is some evidence. What do we actually prove in proof complexity? So we have to use this machine. Well, we use this machinery of bounded arithmetic, which I don't have time to go into. But this kind of backs up what I was saying about understanding proof systems by understanding how much logic you need to prove their soundness. So here I concretely mean how much induction in terms of these bounded arithmetic theories. So the steps look like this. You write down the soundness of G1 as a sentence, just saying it's sound in a suitable language. And then there are well-known results in bounded arithmetic from the 90s. And if you combine them in the right way, you get that this soundness sentence is actually provable in a fairly simple theory that has some kind of base theory. And then it says, every PLS problem has a solution. This will prove soundness of G1. And then there's also this even older machinery for translating these kind of arithmetic proofs into propositional proofs. And if you apply it carefully here, your proof in the previous paragraph, the base theory part turns into some extended resolution derivations. And whenever in the proof you use this axiom that every PLS problem has a solution, you can use an instance of the dominance rule because of the, more or less because of this PLS completeness of the dominance rule. And thus, yeah, you've shown that the G1 is reducible to D. Yeah. So that's an outline of the machinery we need. And let me mention one kind of natural open problem, which is we have this system D, which can do symmetry breaking, although I haven't said why. What if you just look at straight symmetry breaking and try and apply some similar analysis? Do you get that it is stronger than ER or in ER or in between? So with one symmetry, it's in ER. But here is a sort of proposition underlying symmetry breaking. If you have a CNF with some symmetries, then you can write down these extra constraints in the form of CNFs, which kind of break the symmetries, whatever this means. And it preserves satisfiability. Can you do a similar analysis of this? Show some kind of completeness result or something about this search problem of finding a satisfying assignment for here, given one there. Okay, and I'll stop there.
Thank you very much. Questions, Moshe?
There's a suggestion. You may want to look at the concept of BDD proofs.
Of
BDD proofs,
okay.
Which is a proof system developed almost 20 years ago by Atserias, Kolaitis, and myself. And because it seems to me the dominance rule would be some additional rule that looks at the reasoning about the leaves of the BDD.
Okay.
Okay. That looking at earliest assignment, this corresponds to some reasoning about. So this would be interesting extension of BDD proofs by some what I call kind of a frontier level reasoning. And that would be just intuitively seem to be would be analog of the dominance rule. And BDD proofs it's a powerful proof system.
But you're suggesting that BDD could be the same as dominance, or
I'm suggesting that it may be interesting to look
okay,
at the natural variation of dominance for BDD proofs,
okay,
which intuitively seems to me would be some reasoning. So right now the BDD proof is in some sense fully semantical.
Mhm.
This will be getting into kind of inside the BDD package level, which is operations on leaves.
okay.
Usually we don't. Usually we just apply BDDs at the API level. But all the BDD package inside have their own internal API by which manipulating BDDs. Not just take a product or a conjunction in disjunction, negation. This is usually the composition. This is usually the top level API. But inside the B package, there are tree manipulation or BDD manipulation rules. And it seems to me is the dominance would get into that kind of level, trying to have a more fine grain proof system.
Okay, thank
It
you.
looks at internal operations. That's the thought.
Oliver?
Could you perhaps say a few words on the intuition behind the dominance rule, especially the role of this lexicographical order? So yet I don't have a good intuition on that. Just a few sentences.
I think there probably isn't much I can say. Do you mean the intuition on why it is sound, or on why use it, or
What is the meaning of it? So extended resolution, okay, you introduce a
Right.
definition. Okay, so that's the meaning of it.
right?
A new variable which abbreviates a Boolean function.
Uh-huh.
Now, what is the meaning of that rules?
Well, okay. I guess for me at this point, it means a certain way of doing this local minimum search in the
Mhm.
proof system.
I see.
I guess in the paper introducing this particular system,
Mhm.
maybe Jakob could say, but I suppose it looks quite a lot like this Lex leader symmetry breaking
Okay,
principle.
I see.
So they had the same phenomenon that you have a CNF that more or less picks out the lexicographically minimal assignment in a equivalence class under symmetries.
Mhm.
And I guess you get to that from here. I think there were some other applications they had a bit. Though,
Okay, yeah, thank
but,
you. I got an idea. Okay, thank you.
Amana?
So you proved strictly that the D system or G1 is strictly stronger than ER.
well, we proved that
Under which
G is equivalent to
assumption?
G1, which we hope
Yeah,
is stronger than ER.
yeah, yeah. And the assumption is that G1 doesn't collapse to G0,
Yes.
and that would mean second level of polynomial hierarchy wouldn't collapse to the first level. Is there any connection?
I don't think there's any immediate collapse of that kind. I mean,
No,
the
no,
basic
I
the
don't
basic
either.
reason we think G1 is stronger than ER
Mm.
is that we think that reasoning where we can reason about NP properties is stronger than reasoning where we can reason about just polynomial time properties. And we believe this because
Sure.
the same thing is true in classical arithmetic. I sigma 1 is stronger than whatever I delta 0 by consistency statements. But no one has been able to show much about this formally.
So would it suffice to assume that the second level is separated, strictly separated from the first level? Would that suffice in order to conclude that G1 doesn't?
I don't know. It might,
Okay.
but I think that would be some funny technical thing. I'm not
Okay.
sure.
Last question by Bart, please.
In the way the proposition is phrased here, you're making a distinction between gamma and delta, and the delta is derived with extension rules.
Mhm.
The C, will it in the next iteration kind of end up in the delta, or will it really go in gamma? Like you're phrasing a relation between gamma and C?
Well, in the way this is set up, the delta doesn't hang around. Delta is just something that we need to
Mhm.
apply this rule, and then we forget about it completely.
But
So
if you-
what we're changing, yeah, so if we used it, we're changing gamma. We're adding C to gamma.
So in the next application of a dominance rule, you're going to have proof obligations on C as well.
You're going to have,
Proof obligations on the right on C if you apply this rule twice.
yes.
Okay. because that differs from the system in BGMN, where this C.
Yes, so their system is more complicated in that they have kind of two grades of clauses that you derived, and we simplify this by kind of only keeping the basic one. And so we've combined various of their rules together to get this.
Because it's important for if you want to do the symmetry break. Your very last question, like if you have two independent symmetries, yeah, if you do it in the way where the C ends up in the derived set, then it's very easy to do the symmetry breaking twice. But here it might be tricky to do it for two different.
Well, in fact, our full result is that their system, you can simulate it by this with no C. You just take C to be the empty clause. And then you do extended resolution, you do this rule once, and that will simulate their system. So it might be that if you actually try to do it several times, something would go wrong. But to simulate the system, you don't need to.
Okay, it's interesting. Thank you.
Okay, thank you very much again, Neil. We now come to the second talk in this session, which is on small unsatisfiable KCNF with bounded literal occurrence. That's a team from Technical University Vienna, and Stefan Seider will be giving a talk.
Yeah, thank you, Olaf. So let's go to the first slide. I don't know why it is. Somebody tried the clicker. Okay, so this is joint work with my student Tian Wei and with Tomasz. Actually, Tian Wei was supposed to give the talk, but unfortunately her visa didn't work out. So I think she only joins online. Yeah, so what's this talk about? It's about this KSCNF. And accordingly, exists also the KSSAT problem, where the input is a KSCNF. So everybody knows a KCNF. So each clause has K literals. But now we have this additional number S, which bounds how often a variable may occur. So the number of clauses a variable can occur. Very important here, K is the number of distinct literals, exact number of distinct literals per clause. So we are not allowed to have shorter clauses. So like unit clauses are not allowed in KSCNF. And this whole research area started in 1984 with this short but quite influential paper by Dovey. The main observation in his paper is that the 3-3 CNFs are always satisfiable. And if you allow one more occurrence, if you go to 3-4 CNFs, then we already have an NP-hard problem. And so just this lower bound, why 3-3 CNFs are always satisfiable. Dovey used this matching concept. So you draw the incidence graph between the clauses and variables. And by basic graph theoretical notions, one can show that this for a 3-3 CNF, you always have a matching that covers all the clauses. And if you have such a matching, you can now satisfy each clause by choosing the right truth assignment for each variable that's matched to the clause. So therefore, all 3-3 CNFs and actually every KK CNF is always satisfiable. And now we actually already generalized this. It was due to Kratuchwil, Savitsky, and Dusa. They observed that actually for every K, there exists a certain S, the smallest S possible, the value of the function f of k, such that all k f of k CNF formulas are satisfiable, but allowing one more occurrence, the problem jumps from trivial to NP-hard. And in other words, if you want to show that for a particular K and S, the corresponding problem is NP-hard, we only need to find an unsatisfiable KS CNF. because when there is an unsatisfiable one, then we are not in the first case, so it's NP hard. And now it's of course the question, compute this f of k. So asymptotically, after a few iterations in this nice paper by Gebauer, Szabo, and Dados that appeared in Journal of the ACM, they gave a tight asymptotic characterization of this function. But if you have now a particular k and particular s, you don't know whether these asymptotics apply. And therefore, it's the question, how can we compute this f of k? Now, important here is also this notion of, let's call it mu ks, that's the size of the smallest unsatisfiable ksCNF, or infinity if it doesn't exist. And unfortunately, there is no way in general to compute an upper bound on this mu ks. So if we could compute an upper bound, then it would be a finite problem. We could check basically all formulas up to this size, whether they are unsatisfiable or not, and therefore we would have a decision procedure for computing f of k. But unfortunately, there's no way known to compute such an upper bound. Therefore, there is no decision procedure known for computing f of k. So it might actually be an undecidable problem. Now there are two races. There is the f of k race. Given k, find an unsatisfiable k SCNF for an s as small as possible. So when we find the smallest one, when we have computed f of k. And the second race is the mu ks race. Given k and s, find an unsatisfiable k SCNF that is as small as possible with the smallest number of clauses. And in both these races, over the years, some progress has been made. Now just have a look at the f of k race. So here we see that for if k is 3 and 4, the lower and the upper bound match. So we know the exact value of f of 3 and f of 4, but starting from f of 5, it's not known. And so the lower bounds, so these lower bounds are obtained using the matching argument. One can get slightly better lower bounds that apply from k equals 6 onwards using Lova's local lemma. For the upper bounds, for 3, 4, and 5, ad hoc constructions were made, where people just tried to construct an unsatisfiable formula that fulfills these requirements. In 2004, we came up with this general construction, the MU1 calculus, to compute systematically upper bounds. And so the best known upper bounds for this larger case with this MU1 calculus. Actually, when I prepared the slides, I noticed this is exactly 20 years ago. That was times. I remember the time I was a postdoc together with Neil in Toronto. So, and Shlomo Huri, he was also a postdoc at that time in Toronto. Okay, now let's move on to the mu ks race, which is actually for the paper the more important thing. So, and here we look in particular for k equals 3, and we know 4 is the best possible. So we look at k mu 3, 4. Lower bound, you have for k 3 CNF, you need at least 3 variables. And so you have 2 to the 3 different truth assignments, and so you need at least 8 clauses to get an unsatisfied formula. Therefore, we get a trivial lower bound of 8. And in this Dovey paper from '84, he constructed an unsatisfiable formula with 40 clauses, and then Beerman, Kapinski, and Scott in two papers appearing closely after each other, had first a construction with 19 and then one with 16 clauses. But there is still quite a gap between 8 and 16. And one of the results of this paper is that we could show that it's exactly 16. You can't find a smaller unsatisfiable 3, 4 CNF than with 16 clauses. We also look like if you relax, if you allow instead of 4, we allow 5, 6, 7, 8 occurrences, then the size drops. And when you allow 8 or more occurrences, then we are actually at, we meet this lower bound of 8 that we have in general. And then we looked also at mu where k equals 4 and s is 5. So we again have a trivial lower bound of 16. And Stribrunner in her thesis gave a construction with 449 clauses. And Knut, in the Art of Computer Programming, volume 4b, he picked up this problem and he came up with a construction with 257 clauses. And yeah, we also tried to improve this. We could improve it slightly. So there's still, I don't think the 16 is anywhere close to the real thing, but still there is quite some gap. And we also in the paper, we looked at a more fine-grained question when you don't only bound the number of occurrences of a variable, whether the occurrence is positive or negative. We just take the sum of this. We now look in a more fine-grained version when we say a variable may appear at most p times positively and at most q times negatively. And then you can do the same game. You also have these two races, etc. And here we could determine for k equals 3. Now for all possible values of p and q, the smallest unsatisfiable k pq CNF, and there were no unsatisfiable ones exist, which give us also a uniform dichotomy theorem for the complexity of KPQ SAT. So the green areas are polynomial time and the red areas are NP complete. Okay, now this was roughly the main results. Now what are the techniques? I think the interesting about this paper is that we have a theoretical question on SAT, and we use SAT solving to answer this theoretical question. So, and in principle, when you know that certain formulas are always satisfiable, you could actually also build this into a SAT solver to cut maybe some cases quickly. So in principle, it could be a closed cycle. So the difficulties, let's just focus on this one problem to show that the smallest 3, 4 CNF needs 16 clauses. So we can't enumerate all possible 3, 4 CNF formulas up to 16 clauses. 16 looks a small number, but if you just think of the combinatorial explosion, even if you break all symmetries, there are a billion and billion of such formulas. So you can't just list all and check for each is it satisfiable or not. So you need to combine the generation and the testing in one process, so that you don't generate formulas that are satisfied. And so for this, we utilize the SAT modulo symmetries framework. It's originally designed for graphs, but we apply it this way to formulas. A CNF formula we represent by this type of graph. So we have for each literal a node, and the opposite literals are connected. And the nice thing here, if you forgot about the labels, you already break the symmetries whether you flip a variable from positive to negative. So there is some kind of built-in symmetry that when we use this model, we don't need to care about this kind of symmetry anymore. It's built into our graph model. And now we look at the object search. In this case, we search for these formulas as a synthesis problem. Like when we look for a graph with a certain property, we fix the number of vertices, and for each potential edge, we introduce a propositional variable, and then we can express the property into SAT, and then we run the SAT solver to find such a graph. So the idea would be we encode our property, feed it to the SAT solver, and we get the result. However, as I mentioned earlier, we have this combinatorial explosion. We want to break symmetries. So we want to avoid symmetric copies, and one way would be for instance, the incidence graph, you look at the adjacency matrix and look only for lexicographically minimal adjacency matrices. This way, we would break the symmetries. So we could encode this minimality together with the property and run the SAT solver. However, there's a caveat here. It's not known that whether we can encode this minimality with a polynomial size formula. So unfortunately, we can't do this. So therefore, actually, we came up with this SMS framework, SAT modulo symmetries, which similar to a SMT solver, we only encode the property, but then whether it's canonical, whether we have this minimality check, we use an external propagator which checks for a partially defined graph whether it can be extended to a lexicographically minimal graph. And if it can't, we learn a clause that blocks this partially defined graph and feed it back to the SAT solver. Now, here the system gets a little bit more complicated because our property is we have an NP property. Every variable appears at most S times that we can simply encode in SAT. But when we want to encode that the formula is unsatisfiable, unsatisfiability is actually a co-NP property. And so in principle, one could encode it, but again, this would require an exponential encoding. So therefore, we have a second SAT solver where it checks now whether it's satisfiable. And if it's satisfiable, we learn a clause that blocks this co-certificate. And so we can do this with actually this IPA syrup. Armin always corrects me if I don't use this pronunciation interface of Olsted implementing the Cadical solver. So we can do all this using this nice interface. But now, since recently, because this is actually a 2QBF kind of thing that we are solving here, this can be formulated as a 2QBF problem, and we have now ported the SMS framework to QBF. So one can express a property directly in QBF language and does not need to deal with two SAT encodings of the NP and the co-NP part. We can just express it as a in the QBF language. All right, now here are some results in the paper. There are many more tables, but just you get the feeling of the how long this solving takes. This is again for finding a smallest 3-4 CNF that's unsatisfiable. Here we have the number of clauses. We know 16 is the smallest possible. Therefore, only here we get SAT. Everything else is unsat. And here are the number of variables. And the white spots are those where for really easy theoretical considerations, we know there can't be a solution there. So the real ones are the in red. And there are always two numbers, two running times. We know that when we look for a smallest formula, we also know it should not contain any blocked clauses. So we can add to the encoding that there are no blocked clauses. But this encoding is relatively expensive. We have used a lot of clauses to express it. And indeed, for the smaller values, actually the table one could also continue even for to the left side to even smaller values, adding this that there should not be block clauses makes it slower. But interestingly, for larger and larger instances, it pays off even more. And we, in a 5-day running time, we can find this formula with 16 clauses and 12 variables, but without the blocked clause property, we get a timeout. There are actually also this, there's also a timeout here, but fortunately in the paper, we gave some theoretical arguments that if there would be a solution here, then there would already be a solution with smaller values. And actually, the first thing is that there's some very trivial lemmas, And then when we wrote up the proofs, it turned out to be actually require quite some theoretical work to write this down and to figure out avoid, because here we need to solve unsatisfiable, which takes longer than here the satisfiable one. So this would, if we would need to run this to completion, would take quite a long time. But fortunately, with our theoretical arguments, we could kind of get rid of these cases. Right. Yeah, I said this. And now to this was for k equals 3. Now k equals 4 and s equals 5. So here we combine the SMS encoding with this mu1 calculus that I mentioned earlier. What is the mu1 calculus? Very simply said, it's a way of constructing unsatisfiable formulas. So our only axiom is a formula consisting of the empty clause. And our only rule is take two unsatisfiable formulas, take a new variable, and add this new variable positively to some clauses of the one formula and negatively to some clauses of the other formula. And now we have this S bound, so we can only add it in total to S clauses left and right. But this way, so for instance, we have these two trivial formulas, take a new variable X, put X into this clause, not X into that clause, we get the new formula. A new axiom, put Y to some clauses here, not Y here, we get a new formula. And we can continue this, and this way we can construct unsatisfiable formulas. Actually, this construction, we can also identify isomorphic subderivations, and so we can represent this derivation with a directed acyclic graph. So, because we always use it's similar to resolution and deck-like resolution. We just basically collapse things that are reused. And it happens, why is this called mu1 calculus? Because all the formulas that you construct this way are minimally unsatisfiable, mu, and the deficiency, which is the difference between the number of variables and number of clauses, is exactly 1. So mu1 is a very well-studied class. So Oliver, Kleine-Bühning, so there are many papers on mu1. So we know a lot about this. And now this Knut used the mu1 calculus for his formula. And this is the derivation graph of his construction. So again, the only axiom is the empty clause, and then he derives different formulas. And when you do the math, you come to 257 clauses. And so this is too difficult to encode with SMS because we expect the smallest formula, the smallest unsettled for 5 formula to be quite big. So there's no chance to really encode this into SMS. It's just too big. But we thought if we can find for any of these intermediate formulas a smaller one that does the same job, where we can basically replace this in this derivation with the smaller one, then we also make progress. And so we systematically tried all these formulas here, and we expected to be more successful, but there was actually only one that we could compute, was this one, because this has here in Knut's derivation 8 clauses, and we could find one with 7 clauses that does the same job with SMS, which means we don't need to derive this from the axiom, but we just use this basically in this derivation as a new axiom. And now, but why do we get quite few clauses less? Is because this derivation, this is used actually quite often in the derivation. Because remember, this is just a succinct representation of a big tree-like derivation where this axiom is used a number of times. And therefore, overall, we save more clauses. Okay, so that's here now the summary. So we have revisited the KS-SAT and the KPQ-SAT problem. As I showed, it goes back to 1984. We showed exact bounds for the smallest 3S and smallest 3PQ formulas. Our technique in this case was utilizing SMS for CNF formulas. I skipped a few things. It's not completely trivial to use SMS. We need to also to think about some permutations that we can allow and some that we don't allow. So, but in principle, it's SMS. And we could improve the upper bound for smallest 4-5 CNF to 235. And here the technique was a combination of the MU1 calculus with a new axiom that we found with SMS. Some open questions. Of course, this a better upper bound for mu4-5. If you have any ideas, it'd be interesting. Then for the f of k race, as I mentioned, for k equals 5, that's the first one where f of k is not known. It is either 5, 6, or 7. So either knocking off, improving the lower bound from 5 to 6, or the upper bound from 7 to 6, either would be interesting. And there was no progress for 20 years, so over 20 years. So this is something looks doable, right? But one needs maybe a new idea. And because when we actually wrote the conclusion, so we came across that also some people studied the same question, this mu question, but for monotone CNF formulas. That is, all clauses or each clause must be purely positive or purely negative. And then you get different bounds. And there seems to be, for k equals 3, only one open question, namely whether the 3-1-4 CNF, when it's monotone, whether there exists an unsatisfiable formula. I would guess all are satisfiable, but I didn't come up with a proof. And we didn't find with SMS an unsatisfiable 3-1-4 monotone CNF. So this is also an interesting, to say, an exercise or a challenge. It would be interesting to resolve this. Okay, here is again the summary. And if you're interested in using SMS, we have relatively decent documentation on Read the Docs. And I heard that also other people are already using it. Please check it out. I'm happy to answer any questions.
Thank you very much, Stefan. Questions, Moshe?
So there is a natural decision problem. Given KNS, is NP hard or not, right? Do we know whether this is decidable?
You know it isn't decidable?
Is it decidable? What do we know about the decidability? Given KNS, is it NP hard, right? It's a decision problem. What do we know about the decision problem?
We don't know whether it's decidable.
We don't know whether it's decidable. So it's an even that is open.
This is open, yeah.
Okay, so I mean it's important, I think, to list. This is the most fundamental.
Yeah. So there's no, in other words, I said there's no decision procedure known for deciding it.
Yeah.
So in other words, it's undecidable.
But in some sense, it's the most fundamental problem. Okay, just a decision problem for KS. Yeah.
I remember I've talked to Steve Cook about it, and I remember he was very thrilled that this is undecidable, or no, actually undecidable. We don't know whether it's undecidable, but we don't have a decision procedure for it. And,
Okay.
Oliver?
Another open problem seems to me, you didn't mention it, but whether MU1 is enough yields always optimal. results or not. Now, your last images seem to indicate first evidence that MU1 might not be enough. Namely, you step with your new axiom beyond MU1. Do you have any? So, do you consider this an interesting question, or?
Yeah, it's an interesting question, definitely. So we know that for the FK for MU1, we can, when we just restrict ourselves to the class of MU1, then it's decidable.
Yeah.
And so but we know that the bound, the F bound we get from MU1 is not tight. So the real one is smaller. But for the smallest formulas, in particular for I think k equals 4, it could be the case that MU1 and general CNF match, but we don't have a proof for this. But it's an interesting point.
Yeah, thank you.
Any more questions? Well, maybe I can ask one. So you mentioned that you can use both SAT or QBF to solve this problem. Did you try both? And if so, which was better?
So SAT and it's the SMS framework. We can either use basically because it's in principle it's a 2 QBF problem, and so you can use 2 SAT solvers, one for the existential player, one for the universal player, or you can use a QBF solver, which actually itself might also use 2 SAT solvers. So here I think just out of simplicity, we use this new QBF formulation of the problem. But in principle, whether you use 2 SAT solvers or 1 QBF solver, in principle, it should be more or less the same. You might get a little bit of mileage when you do the 2 SAT solvers because you can do a bit more like hand tuning to it, but you lose the nice uniformity of the QBF formulation, for which since recently we also have a uniform QBF proof when we get unsatisfiability. So there are a lot of benefits of using the QBF solver, which I could imagine you can also relate to.
Okay, thank you very much. Thanks again, Stefan.
Thank you.
So we now come to the final talk in this session. Sergey. Talk is on symbolic limits of symbolic approach to SAT solving. This is joint work by Dimitri Itsykson and Sergey Ofrarov. And Sergey will be giving the talk, please.
Thank you for the introduction. I would like to begin with a short introduction. So in our work, we prove lower bounds for SAT solving algorithms. We consider symbolic approach to SAT solving. The key idea of symbolic approaches is to gradually convert an input CNF formula to a representation model where satisfiability can be checked efficiently, and then check satisfiability. And in our work, we consider OBDD, stands for Ordered Binary Decision Diagram, as a representation model. So let me define what OBDD is. But first, I need to define branching program. So you can think about branching program as some data structure to represent a Boolean function. So let X be a set of Boolean variables. A branching program as a directed acyclic graph with one source and 2 sinks. Each non-sink node is labeled with a variable from X and has 2 outgoing edges. One is labeled with 0 and the other with 1. And one sink is labeled with 0 and the other with 1. Each assignment into X induces a path from the source to a sink. And the sink in which this path ends stores the output. So in 1986, Bryant proposed an important special case called OBDD. So it's just branching program, but we have a restriction that variables on the passes from the source to sinks appear in the same order. On one hand, this restriction reduces computational power of diagrams, but on the other hand, now we can do many useful things efficiently. So for example, we can minimize OBDDs, check the satisfiability efficiently, take conjunction of two OBDDs in the same order, change variables order, and other things. And also, it's important for us that clauses have small OBDD representations. And again, in our work, we use OBDDs to represent Boolean functions. So now I define the main subject matter of our work, OBDD algorithms for SAT solving. So let phi be a CNF formula. We initialize set S as the set of all phi's clauses. Then we choose some variables order pi over phi's variables and initialize a pi OBDD as a constant rule, pi OBDD. Then, while S is not empty, we apply one of the following rules. So the first rule is a conjunction rule. It allows us to take a clause C from S, delete it from S, and add it to D. So replace D with a pi OBDD for D and C. The second rule is a projection rule. It allows us to take D and replace it with a pi OBDD for exists XD. But it's important that we can apply this rule only if S does not contain clauses with X anymore. So all clauses with X are already downloaded into D. And the third rule is the reordering rule. It allows us to take to change variables order in D. So change pi. And at the end of the algorithm, when S is empty, we say that phi is satisfiable if and only if D is satisfiable. So actually, we have not one, but a family of algorithms. And in brackets, we list rules we are allowed to use. And also, so how do we measure complexity of the algorithm? We measure it by the size of its execution track. And an execution track is a sequence of OBDDs constructed by the algorithm during its runtime. So let's see an example of OBDD algorithm. So suppose we have this formula phi. Then possible execution track of OBDD join exists algorithm can look like this. So we take the second clause, compute OBDD for it. Then we add the third clause. Then we can now apply a projection over X variable because the remaining clause does not contain X. And then we add the third clause into OBDD. And you may notice that actually at the end of the algorithm, we obtained OBDD for exist X phi. So at the end of the algorithm, we check satisfiability of exist X phi, but it's the same as satisfiability for phi. And so you may wonder why we use these projections, because in some cases, if we choose projections order wisely, we can reduce execution track size. So for example, it is known that pigeonhole principle is hard for BDD join algorithms and even for join reordering algorithms. But at the same time, pigeonhole principle is easy for BDD join exists algorithms with projections. Okay. A few words about OBDD algorithms. So it's the main subject matter of our paper. It is a scheme of algorithm, not a specific algorithm. So each specific algorithm must decide how it chooses clauses, makes projections, etc. And when we prove lower bounds for a scheme of algorithm, we prove it for each specific algorithm that follows the scheme. Also, it's important that OBDD algorithms can be performed efficiently inside of the execution track, because we can perform operations with OBDDs efficiently. And we are interested in lower bounds for OBDD algorithms, as I said earlier. So this question was studied before. For example, lower bounds for OBDD join exist algorithms follows from the lower bounds for OBDD join exists proof systems. But also it's known that a reordering rule makes OBDD algorithms stronger. So proving lower bounds for reordering algorithms is a more challenging task problem. However, exponential lower bounds for OBDD join exist reordering algorithms on satisfiable formulas are known, but for some artificial formulas that are characteristic functions of error correcting codes. But I must say that specifically for OBDDs, proving lower bounds on satisfiable formulas is easier than on unsatisfiable in some sense. Because, so imagine phi is a hard unsatisfiable formula, then we can consider formula x of phi. We add a new variable x to every clause of phi. And we can show that this is a hard satisfiable formula. And we don't know similar reductions the other way around. So we can derive lower bounds for satisfiable formulas from lower bounds for unsatisfiable formulas. And in our work, we propose two different lower bounds for BDD join exist reordering algorithms on unsatisfiable formulas. So that was an open question before. So let me tell you about these lower bounds. So the first approach is the following. We proved this theorem. So let phi be a satisfiable formula hard for OBDD join exist reordering algorithms. So let psi be an unsatisfiable formula hard for OBDD join reordering algorithms without projections. And then there exists some formula f from phi psi. I will define it a bit later. That is unsatisfiable and it's hard for BDD join exist reordering algorithm. So what we want. Exponential lower bounds for BDD join exist reordering algorithms on satisfiable formulas are known. As I said, exponential lower bounds for BDD join reordering algorithms on unsatisfiable formulas are also known. And hence we use this theorem and combine these lower bounds and obtain desired lower bounds for BDD join exist reordering algorithms. That will also be exponential. So a short proof plan. So we define f from phi psi as follows. We simply take psi formula and add some new CNF t. And t is this thing. So we basically take many copies of phi, add x variables to each clause, and conjunct it all. Clearly, this formula is unsatisfiable because it contains psi as subformula. But so why is this formula hard? Because each algorithm during its runtime either do not apply projections over x, y variables, but we can show that in this case it must simulate OBD join reordering algorithm on psi. But psi is hard for such algorithms. Or it do apply projection over x variables, but then it by our restriction must first download all clauses with X, Y into like OBDD. But that we can show that in some sense it must first run on phi formula. But phi is hard for OBDD join exist reordering algorithms, and again, hence the lower bounds. Okay, a few words about this approach. So actually using this approach, we can get a stronger result. For this, we consider one NBPs, stands for read once non-deterministic branching program. You can think about it as some generalization of OBDDs. But now some nodes are guessing, so non-deterministic. And also instead of order restriction, we have a restriction that each path from the source to sink contains every variable at most once. And we also can define one NBP algorithms, just like OBDD algorithms, but one with one NBPs instead. And now we don't have the reordering rule because there is no order in one NBPs. So sadly, it is a purely theoretical notion, so most likely we cannot implement them like in practice efficiently. But our approach allows constructing hard unsatisfiable formulas for one NBP join exist algorithms from hard unsatisfiable formulas for one NBP join algorithms and hard satisfiable formula for one NBP join exist algorithm. Okay, so it's basically the same theorem, but with one NBPs instead of OBDDs. So you may wonder why we consider these purely theoretical things. So here is why. Because there is this result by Sigerlind that OBDD join exist algorithms do not simulate deck-like resolution. And using our result with one NBPs, we can extend this theorem. So we prove that there is a family of CNFs of polynomial size that has polynomial size tree-like resolution refutation. But any execution track of one NBP join exists algorithm on these formulas contains one NBP of exponential size. So in other words, one NBP join exists algorithms do not simulate tree-like resolution. And as a corollary, we obtain that OBDD join reordering algorithms do not simulate tree-like resolution either. Okay, so why we? So here is a proof idea. We consider extended versions of tree-like resolution and extended version of one NBP algorithms. And it is known that extended tree-like resolution is very strong proof system. And at the same time, extended one NBP algorithms is equivalent to simple one NBP algorithms. So no profit. And we use a hard formula that we derived earlier. So hard for one NBP algorithms to prove this separation. So it is hard for one NBP algorithms, but we can show that it is easy for extended resolution. Okay, that's all for the first approach. And the second approach, we prove lower bounds for binary pigeonhole principal formula. So I will define it. So let n be a power of 2. We consider a variables matrix with n+1 rows and r columns. And BPHP formula encodes that all rows of the matrix are distant binary strings. It is clearly unsatisfiable because there are only n distant binary strings of size r, but we want n+1. Also, it can be encoded efficiently as CNF. And so we prove these lower bounds. that there exists epsilon such that the execution track of any OBDD join exists reordering algorithm on the input BPHP contains an OBDD of size at least 2 to n2 epsilon. Well, actually, it's all for the second approach because the proof is rather technical, so technically hard, and I will not talk about it now. So in conclusion, I want to make a summary of our results and compare them. So lower bounds for so-called F from F5 psi formulas. So on one hand, it is very artificial formulas, but on the other hand, the proof is rather easy. And also it helps us prove that OBDD join exists reordering algorithm do not simulate tree-like resolution. And lower bounds for BPHP, so binary pigeonhole principle formula. So it's natural formulas, but the proof is technically hard. Okay, and in conclusion, I want to highlight some open questions that are related to our work. So the first open question is to prove a super polynomial lower bounds for the OBDD join exist reordering proof system. So in our work, we considered algorithms and this is proof system. And the second open question is to understand if BPHP formula hard for OBDD join exists, maybe without reordering proof system. Okay, so that's all I wanted to say. Thank you for your attention, and I would be glad to answer your questions.
Thank you very much. Questions? Moshe again first.
So the algorithm you're considering, I would call them sequential algorithms. They kind of produce monotonically by adding more and more clauses. But a few years later, Gochan Pan and I studied tree-like algorithms that do not proceed sequentially, and they are much more competitive with sequential algorithms. So have you looked to try to prove lower bounds for more realistic OBDD algorithms?
Thank you for your question. So in our work, we only considered algorithms that add clauses one by one, so sequential. So I don't actually know what. So is it same lower bounds works for non-sequential algorithms? So I believe.
Well, we know, for example, that pigeonhole principle can be done efficiently. There are short polynomial proofs for pigeonhole principle using BDD proofs. Just if you look at it as a proof system, not algorithmic. There is a question here, for example, whether the algorithms can handle PHP. Okay. But again, if you want to look at BDD algorithms, I think these are, I would call them the 2000 class algorithms or before, and they are now much better algorithm. And in fact, even there's been more progress since I did this work, which was almost 20 years ago, which using also 3D compositions on the formula. Mm-hmm. And that's a direction you may want to look at.
Okay. Yeah, I will think about it. Thank you.
Any more questions, comments? Yeah, there's a question over there.
Yeah, I just had a question. You said that the lower bound for OBDD proof system is there's some known gap between that and the lower bounds for the OBDD algos. Can you give me some intuition on that? If I'm understanding you correctly.
Sorry, can you repeat this? So what intuition?
Yeah, so you had said that at some point that the word bound on the OBDD proof system Is there any gap between the lower bound that you found for the algorithms and the lower bound that you can just arrive via the proof system without doing any reordering?
So what proof system? Like the several proof systems.
OBDD proof system, the original OBDD proof system without.
Yeah, but the like OBDD join exists proof system or join exists reordering proof system.
Yeah. No, without the reordering one.
Yes. So and what again the question with? So which slide?
No, so I'm asking. At some point, you had mentioned that I mean, is there like you talked about there being some sort of a gap between the lower bound for the OBDD proof system without like as in does reordering necessarily give us lowered lower bound? Do we know that reordering itself is adding a lot of succinctness to the length of the proof or the length of the track? Is there any known gap kind of a thing there? Like if I don't have reordering in OBDD, do I lose something like drastically?
Okay, so about gap between proof systems and algorithms.
Either the length of the algorithm track or the proof system. I mean, is there anything known? Does reordering give us any more power?
Okay, yeah, thank you. So about reordering, yes, reordering gives us more power, and for both algorithms and both proof systems, and with projections and without projections. So join reordering proof systems are stronger than just join proof systems, and so on. Did I answer your questions or?
Yeah, let's take it offline.
Okay, thank you.
Okay, any last question? Well, if not, then thank you again, Dimitri. And we now go into the lunch break until 2 o'clock. Lunch will be provided on the premises, I guess, at the same place where we had lunch yesterday, which is just very close by. And see you back at 2.
Small set of announcements, please. Again, the Wi-Fi details are in your kit. There's a help desk just outside in case you need anything. No photography allowed, no beverages and food allowed inside the MPH. Also, one thing you might have seen, these new devices have popped up all of a sudden yesterday, right, on the side. So there's going to be a very interesting Indian cultural program today after today's sessions are over. So I highly recommend you have a look, enjoy the particular program. Since we all are from theoretical background, there are whiteboards and markers placed at various places. Please get in touch with the volunteers in case you want to have any impromptu discussions. And for the next session chairs, Nidhi is going to make some announcements.
Yeah, hi. I would like to request the session chair for the next session, Mr. Alexander Narel, and the speakers who are going to present for structure-based symmetry breaking in SAT, causal congruence closure, and lazy reimplication in chronological backtracking to please stay back for the arrangement of the slides and speakers, please. Thank you.
Diganto. Next. Next. Hello, hello. Hello. Can you hear me? Hello. Hello. Can you hear me? Hello. Hello. Hello, hello, hello. इसका माइक का इशू है नक्षत्र
Hello. I had this already 5 hours, right? Different than the ones we had. Ah, it's bendable. This one is bendable, so this is cool. Right? Test, test, test. So it's working, right? 1, 2, 3. So this is working.
Hello, hello.
Hello.
Hello, hello. Hello. Echo. It's working. Okay.